All right, so the last thing that we want to talk about, that we need to talk about out of this chapter, is how does all of this play into equilibrium? So, while we've largely steered away from equilibrium, um, we're going to have to talk about it again here because, as we just saw in the previous examples, there are some circumstances where we have to deal with reversibility, and equilibrium does help us to establish kind of a point between spontaneous and non-spontaneous. That being said, we're going to go back to a simpler form of equilibrium where we don't really have to do a whole lot of ice tabling. It's more just about a matter of the equilibrium expression and using Q to figure out where we are in relationship to the overall equilibrium. And we got to start with the main idea here is that our calculation for free energy is only a standard calculation if the reactants and products are all in their standard states. And so under standard conditions, that would mean that we're going to expect to see some form of directionality in the reaction until we get to equilibrium itself. And so just as an example here, if we're looking at the vaporization of water, where water is going from the liquid phase to the gas, the standard enthalpy, or excuse me, the standard free energy of reaction here is a positive 8.59 kilojoules per mole. And that makes sense to us. We know that we have to input energy. Water does not turn into gas, at least not very well, at 25 degrees Celsius, at 298 Kelvin. We get some vaporization from evaporation, but on the whole, the majority of the water is going to stay as, well, liquid. If we're not at standard conditions, we can calculate delta G from the standard conditions by adding a correction term. The correction term is this, RT times the natural log of Q, the equilibrium, the reaction quotient. Give us an idea of products versus reactants here. And so if we're at standard conditions, just think about this reaction that we're looking at here. If we're at standard conditions, Q would be equal to the pressure of water in the gas phase. And if we're at standard conditions, that would be 1 atmosphere. So Q would equal 1. Natural log of 1 is 0, and that term would completely go away. We'd be at standard conditions. We wouldn't need to calculate further. But if we're not at standard conditions, if we are at this condition right now, well, how much gas pressure is there? What is the concentration of gaseous water in the atmosphere? Those are questions that we would have to answer to figure out our actual position, as opposed to our standard position. And this is also how we could manipulate the equilibrium or manipulate the reaction to get us toward an equilibrium state. So just as a reminder of kind of what equilibrium looks like, and now putting it in terms of free energy, when we have Q less than K, meaning that we've got a reactant favored system, what we're going to see is we're going to see spontaneity moving toward product until we get to that desired equilibrium point. And at that desired equilibrium point, delta G is going to equal 0. We're going to be at K at equilibrium. And when Q is greater than K, and we have more product than anticipated, more product than expected, we see that shift toward the left. We see a shift toward reactants until we hit that equilibrium point. which means that the reaction in the forward direction would not be spontaneous, but the reaction in the reverse would be. And so, generally speaking, every chemical reaction ends in one place. And that one place is equilibrium. So if we compare our current conditions to what equilibrium conditions are, we can predict which way the reaction is going to be spontaneous or non-spontaneous until we get to that equilibrium point. From there, we can make those kinds of determinations. But every reaction ends at the same place. It ends at some form of equilibrium. It's just a matter of where is that equilibrium? Is that equilibrium extremely product favored, extremely reactant favored, or is it somewhere kind of in the middle? And so our interpretation of the interplay between Q and K and delta G goes like this. If I have a forward reaction that is spontaneous, meaning delta G is negative, well, in that case, what we're seeing is that we are currently not at equilibrium, and we are shifting toward the products to get that way. And so what we're going to see experimentally is that the reaction is product favored, at least at these conditions at this moment. And if we see that delta G is positive, what that means is that the reverse reaction is favored. The reverse reaction is going to move things from product to reactant. We're going to have a reactant favored equilibrium, reactant favored reaction until we hit that equilibrium point again. And then finally, when delta G is at zero, then we truly are at equilibrium. Neither the product favored or the reactant favored reaction is more prominent than the other. We have true equilibrium. Q is equal to K. But the point that we want to stress and the point that we want to hammer home about this is that all reactions drive toward equilibrium. And since all reactions drive toward equilibrium, then we can get a reasonable kind of feel for what we talked about in terms of extent and how that relates to spontaneity. So if we go all the way back to chapter 13, talked about the idea of equilibrium as just this overall construct. And we talked about the value of equilibrium, the magnitude of equilibrium. When K is big, it means this. When K is little, it means that. We can use that same kind of argument now to talk about spontaneity. When K is large, what does it mean for delta G? When K is small, what does it mean for delta G? And so there are some equations that we can throw in here that'll help us out. So we've already introduced this equation. How do I determine delta G if I'm not at standard conditions? This secondary equation is kind of born out of that first one. And it concerns the idea of, okay, well, what happens if Q is equal to K and delta G is zero because we're at equilibrium? Well, in that case, we can substitute and start to calculate. And where we end up is that we get delta G as being equal to R times T times the natural log of K. Delta G is the standard free energy. R is our gas constant. Notice the value of gas constant we're using here is 8.314 because we are talking about energy here. Temperature is in Kelvin, and the capital K there is the equilibrium constant. Somebody didn't do their algebra right. In your notes, make sure that you drop a negative sign in here. So delta G at standard conditions is equal to negative R times T times the natural log of K. And so what does this mean? Well, when K is greater than 1, which we have called product favored all throughout equilibrium unit, well, if K is greater than 1, that means that the natural log term is going to be positive. The end result of that is that we're going to get a calculation for delta G that is negative, meaning that the reaction is spontaneous. And when K is less than 1, what we used to call reactant favored, then delta G will be positive. And our interpretation of that would be that it is non-spontaneous. So you might have seen as I inadvertently clicked to the next slide, this table basically summarizes that here fully. When delta G is negative, K is going to be greater than 1. What does that mean? It means that our reaction is product favored. For a reaction is spontaneous, we're going to find products at the equilibrium point, much more so than reactants. When delta G is positive, then we're going to find that the reverse reaction is spontaneous. We're going to see something that's reactant favored. And so if you start putting this into the context of some of the things that we've already seen, what kinds of reactions were reactant favored? Most of the ones that we've been working with over the past couple of weeks. Weak acid equilibria, weak base equilibria, things like salt solubility for insoluble salts. KSP values being extremely low. Why is that the case? Well, because that reaction in the forward direction is not very spontaneous. In fact, it's non-spontaneous. The reverse reaction is much more spontaneous, getting the solid and not the ions. If delta G is 0, then what we have here is a value of K of 1, and that's the rare case where we have reactants and products that are not favored at all. Now, most reactions don't behave in that kind of way. The only times where we will tend to see anything that closely resembles that are phase changes. But again, phase changes are designed to only occur at one set temperature. So delta G under standard conditions isn't going to be zero. Delta G at whatever that condition happens to be will be zero. So let's do a couple of practice problems where we kind of put this into action. So I've got the reaction between nitrogen dioxide and itself to make dinitrogen tetroxide. First thing I need to do, I need to determine the value of delta G at 298 Kelvin. Second thing I want to do is I want to determine the value of delta G if we have these partial pressure values instead of standard conditions. Now, to answer the first question about delta G, we're going to have to use delta G of formation values. So delta G at standard conditions for the reaction is going to be the free energy of formation for dinitrogen tetroxide minus 2 times the free energy of formation for the nitrogen dioxide. We just need to look those values up. So going to nitrogen in the table. So nitrogen dioxide in the gas phase is positive 52. And N2O4 in the gas phase is positive 98. So 98 minus 2 times 52 is negative 6 kilojoules. So this reaction is spontaneous at room temperature. Now, to answer the second question, delta G is equal to standard delta G plus RT natural log of Q. We have the delta G value, negative 6 kilojoules. R is 8.314 joules per mole Kelvin. Temperature, 298 Kelvin. We aren't changing the temperature condition. We're just changing the reaction conditions. Q, products over reactants. So 1.60 atmospheres divided by 0.4 atmospheres. And since there are 2 nitrogen dioxides, we're going to square that term. We do have a unit mismatch. So 6 kilojoules and that here. So let's move this over. Negative 6,000 joules. 1.6 divided by 0.4 squared. Inside of the parentheses, it's 10. So the natural log of 10 multiplied by 298 multiplied by 8.314. And we get to 3 significant figures, 5,700 joules. So delta G is negative 300 joules. And so what does that tell us? Tells us that the reaction is still spontaneous in the forward direction at these conditions, but it is approaching equilibrium. So the standard condition would have had 1 atmosphere in the numerator, 1 atmosphere squared in the denominator. We have moved more toward the products, but we can see from the calculation here that we still have more room to go. All right, any questions with this example? All right, let's open up this kind of question in Top Hat then. So this time what we are doing is we're using a different calculation here. So we're not trying to figure out position of the equilibrium and is it spontaneous or not. We're using this equation here. The only thing that we have to do is we don't have a delta G value yet. We're gonna have to calculate that. And what's our equilibrium expression look like for this reaction? I'm going to calculate K. What do I need to put on the top? What do I need to put on the bottom? No. If I'm looking at the equilibrium expression, so the concentration of the products over the concentration of the reactants. Okay. Anything else? No. Barium oxide's a solid, so it's left out. Barium carbonate's a solid, so it's left out. This is how we can answer that question directly. Since K is the concentration of carbon dioxide, or if we're looking at Kp, the pressure of carbon dioxide, either way it works. It's the same value in this case. So start by figuring out what delta G is, then use those values to figure out what K is at those two different temperatures. Right, so we can start with the calculation for delta G. So it's products minus reactants. So delta G would be negative 528.4 plus negative 394 minus negative 1138. So putting those together, and rounding to the ones place, we would get positive 216 kilojoules. And again, this kind of thing, should make sense. This is a decomposition reaction. It's going to require energy input to run. So the idea that it's not spontaneous just on its own, makes some sense. Now we just need to include it in our calculations for the two different temperature conditions. So for condition one, we have 216,000 joules equal to negative 8.314 times 298 Kelvin and the natural log of K. So I do my dividing, 216,000 divided by negative 8.314 divided by 298. And to three significant figures, I get negative 87.2 for the natural log of K. Use E to get rid of the natural log. And I get K at 1.37 times 10 to the negative 38th. And since that is the pressure of the carbon dioxide, the unit would also carry over as atmospheres. Now, 1.37 times 10 to the negative 38th atmospheres, practically zero. If we do this reaction at 1100 Kelvin instead, set up exactly the same way. $216,000 divided by 8.314 divided by 1100. This time I get negative 23.6. E to both of those. I now get a K value of 5.53 times 10 to the negative 11. So again, not a terribly large sum of carbon dioxide, but certainly considerably more than what we had at 298 Kelvin. So at some point, the question would need to be begged, well, at what temperature do we finally actually get to see an appreciable amount of carbon dioxide? And that's where you would use that other equation. Where if we go back to here, okay, at standard conditions, it's incredibly unfavorable. What would it take to be incredibly, to make it at least favorable or at least at equilibrium? And for that, we would have to start manipulating the temperature a lot more. And we'd also have to start manipulating, well, you can't start with more than zero carbon dioxide, but you know. All right, last thing that we want to talk about. We saw this already when we talked about equilibrium kind of overall. The idea that the temperature dependence of the equilibrium constant is real. And we saw with the Van 't Hoff equation in chapter 13 that we could relate enthalpy to the value of our equilibrium constants and temperatures. Well, if we take this one step further, We can plot a similar kind of course using the natural log of K as our Y and 1 over temperature as our X. And what we'll focus on is now we have context for the enthalpy being related to slope, which we already knew. But now we actually have a context for entropy being related to the intercept. And so if we plot a graph of equilibrium constants versus temperatures, the result of that graph would give us both pieces of information that we were interested in. And what it does is that here are a couple of examples. So here I have an exothermic reaction where delta H is negative, and I can see that I have a positive slope on the graph because the negative of a negative would give us a positive. And in this case, our intercept is negative, which tells us that delta S is negative. But there would also be versions of this where delta S, the y-intercept, crosses above the x-axis where it is positive. And in those cases, what we would have is we'd have a situation where it's always spontaneous because delta S is favorable and delta H is favorable. And here we have a circumstance where we have a negative slope, which indicates that the reaction is endothermic. And again, it is crossing in negative territory. So that means that delta S is negative as well. And what this particular plot would show is that this particular reaction is never spontaneous. Because if it's got an unfavorable delta H and an unfavorable delta S, it's not a spontaneous reaction. It never will be. It will always be reactant driven. Now, like we saw in earlier units, the Van't Hoff equation, the 2-point formula for the Van't Hoff equation, we can use that to figure out the value of delta H if we just have 2 temperature points. We did that in chapter 13. We also did it in lab. And if we have that information, we can easily calculate delta S based off of enthalpy and free energy values. So if we don't have enough data points to fully do a graph of the data like what we saw in the previous slide, we can still get around it with 2 data points. And with 2 data points, we can figure out delta H from the Van't Hoff equation and delta S using free energy of formation values, along with that delta H and the temperature. And that's it for thermodynamics. So go ahead and get your last participation point for this chapter. Are there any questions about free energy or free energy and its relationship to equilibrium, the stuff that we talked about today?